When a massive star depletes its nuclear fuel, the outward push of fusion stops. Gravity takes over. The core's internal support, known as electron degeneracy pressure, fails, and the star's mass goes into a catastrophic gravitational freefall. The inward collapse rebounds off the dense center, blasting the outer layers into space. What remains in the center of this wreckage, like the remnant forming inside supernova 1987A seen here, is a neutron star. This creates an environment where matter is subjected to pressures we cannot replicate on Earth. Inside this newly formed sphere, standard atomic bonds no longer exist. The electrons have been crushed into the protons. The star's continued survival relies entirely on the mechanics of raw nuclear physics. This is an object packing up to 2 times the mass of our Sun into a sphere barely 10 to 20 kilometers across. If you placed a neutron star over Manhattan, its physical footprint would barely cover the island, yet its surface gravity is 2 billion times stronger than Earth's. To model how matter behaves under this level of extreme compression, physicists use a mathematical framework called the equation of state. This graph maps the direct relationship between the density of nuclear matter and the outward pressure it generates. The shape and slope of this curve represents the stiffness of the matter. If you keep adding mass to the star, the density increases, pushing the curve higher until it hits a hard mathematical ceiling, the Tolman-Oppenheimer-Volkoff, or TOV limit. Past that limit, the nuclear pressure can no longer hold. The equation of state defines the exact threshold where a neutron star loses its structural integrity and collapses inward to form a black hole. Moving downward from the surface, increasing density breaks matter down. Past 2 billion Gs of gravity, the outer crust forms a rigid crystalline lattice of heavy atomic nuclei. Under high pressure, stripped electrons create a dense flowing sea that permeates the lattice. At these low relative temperatures and high densities, these electrons form Cooper pairs. They enter a state of electron superconductivity, allowing electrical currents, heat, and magnetic fields to move through the outer layers without resistance. Descend deeper into the inner crust, and the pressure crosses a critical boundary. Saturated atomic nuclei can no longer hold neutrons, which physically leak into surrounding space. Further down, proton repulsion fights the strong nuclear force, deforming these dripping nuclei. They stretch and flatten into geometric rods, slabs, and tubes, called nuclear pasta. Past the pasta layer, empty space is gone. Physical properties are dictated completely by the strong nuclear force. Crossing into the outer core, the structures dissolve entirely. Protons and electrons merge, leaving an incredibly dense, uniform fluid of closely packed neutrons. The star's ability to support its own weight now relies on a quantum mechanical rule called the Pauli exclusion principle. This dictates identical fermions, like neutrons, cannot occupy the exact same quantum state. Forcing them together generates a powerful outward resistance known as neutron degeneracy pressure. But degeneracy pressure alone cannot hold up a massive star. As neutrons are squeezed closer, the strong nuclear force, which normally binds particles together, flips. At these extreme densities, it becomes fiercely repulsive, providing the primary outward push against gravity. To calculate the stiffness of this neutron fluid, physicists use models like chiral effective field theory. By mapping the symmetries of the strong nuclear force, this model plots how much resistance the core provides, directly shaping the theoretical mass-radius curve. The geometric size and structural stability of an object heavier than the Sun is maintained entirely by a microscopic rule governing subatomic particles. Beyond fighting gravity, the core must also shed the immense heat left over from the supernova. In its first few thousands of years, a neutron star cools at an incredibly rapid pace. This cooling is driven by weak subatomic interactions called Urca processes. In the direct Urca process, a neutron decays into a proton, expelling an electron and an electron antineutrino. The antineutrinos pass cleanly through the dense matter, carrying thermal energy into space. If the central density isn't high enough to support the direct process, the star relies on the modified Urca process. This requires an extra nucleon to transfer momentum, making it less efficient and resulting in a slower cooling rate. As the core cools, a severe phase transition occurs. Bound Cooper pairs turn the dense matter into a superfluid, which flows entirely without friction. Binding the particles into Cooper pairs locks them up, heavily suppressing both the direct and modified Urca reactions. The mass emission of neutrinos drops off, and the star's cooling curve flattens out over the next few millennia. A quantum state, achieved in the deep interior, acts as a physical throttle, regulating the thermal evolution of the entire star. Plunging into the deepest layers of the inner core, we reach densities that exceed normal nuclear saturation by several multiples. Under this crushing weight, standard protons and neutrons lose their structural integrity. Theoretical models suggest they break down into exotic phases, such as hyperonic matter. Hyperons are heavy baryons that contain at least one strange quark. Strange quarks don't exist in stable matter on Earth, but the extreme pressure at the center of a neutron star provides the required energy levels for them to emerge. Alongside hyperons, the core might also generate meson condensates, or dissolve entirely into a fluid of deconfined, free-floating quarks. Look back at the equation of state graph. These exotic particles absorb energy that would otherwise contribute to outward pressure, softening the equation of state. As the pressure curve drops, the maximum mass the star can support drops with it. If strange quarks form in the inner core, the neutron star loses structural rigidity. A mass stable under a stiff equation of state might suddenly cross the TOV limit, initiating an irreversible collapse into a black hole. Zooming back out to the surface, the internal quantum mechanics manifest externally as one of the most hostile electromagnetic environments in the universe. When the original massive star collapsed, its geometric size shrank drastically, but its total magnetic field did not. The field lines were compressed and concentrated, a principle called magnetic flux conservation. During the first moments of core collapse, the rapid rotation of the star combined with turbulent fluid dynamics inside the core. This dynamo effect acts as an amplifier, driving the magnetic field up to a quadrillion Gauss, creating a class of objects known as magnetars. These intense magnetic fields are anchored in the superconducting crust we mapped earlier. As the star spins, these fields whip charged particles through space, generating the periodic radio pulses and massive X-ray flares that telescopes detect. Every time an observatory measures a pulsar's timing, detects a surface X-ray burst, or records gravitational waves from a neutron-star merger, a new data point is plotted. This observational data directly tests our math, tightening the constraints on our theoretical equation of state. By tracking the thermal and electromagnetic outputs of these distant, dense spheres, we are systematically reverse engineering the behavior of the strong nuclear force itself.